Hi, my name is Prakash Mitra, and this is my Lab 2 Physics 2211 projectile motion. Introduction. The purpose of this lab is to observe and analyze projectile motion. Another purpose of this lab is to compare computational models calculated through glow scripts, comparing a model with drag force and one without. The fundamental principles in this lab are Newton's second law, constant force, and drag force. Preview. The system in this lab experiment is the paper wad, and the surroundings is the earth and air. By the end of this lab, it will be shown that the computational model with drag will match experimental data. And the computational model without drag will have the x component velocity remain constant and the y component velocity decrease due to gravity. This is a video of my lab experiment. Okay, and this is my tracker data. So on the left, we can see the table of the time of my experiment and the x and y positioning of the paper wad plotted. And on the right, we can see the graphs of the x and y position accordingly. On the top is the x position with respect to time, and on the bottom is the y position with respect to time. And this is my glow script code and calculations for models. So my data that I used was that the initial time was 0 seconds and the final time was 1.102 seconds. So that means the whole time in my experiment took 1.102 seconds. For my drag force constant, I used 0.2 for the computational model with drag and then 0 for the computational model without drag. And my drag force was calculated with negative b times v squared times v hat. And the force of gravity is 0, negative mg, 0. And my Fnet was calculated through Fg plus F drag. And I used the momentum principle with the velocity and position update formulas, which is Newton's second law. And then the arrows were drawn with drag opposite of motion, and gravity always pointing towards the negative y direction, and velocity following trajectory. And these screenshots show my glow script code. And this is my computational models with drag. So as we can see, the picture of the model shows the ball going below the origin or the surface. And this is because in my experiment, I launched the ball at a height instead of launching it from the ground. So the ball ends up below, I guess, the origin, as I set my calibration and my origin at the ball and not the ground. So because the ball travels below the origin, that's why it looks like the ball's going underneath the surface. And this is my computational model without drag. And these are all the models together. So as we can see, there's some discrepancy between the experimental data and the computational model with drag, which we'll get into in the sources of error. But yeah, these are all my graphs together. And so some sources of error, what may have been the calibration stick matching up in tracker, where I might have not made exactly 1 meter as my distance. And tracking the projectile motion of the paper wad might have gone astray, as I might have not exactly clicked the center of the paper wad every time I had to track the motion. And also tracking displacement with software may have led to an unseen error. But also another big source of error is that maybe if I made the origin the ground, maybe the graph would have been translated up 1 unit, so maybe it would look more like the computational model with drag, as we can see in this graph. So maybe that may have led to a different outcome. So what does it mean? The terminal velocity happens when a free-falling object experiences 0 net force. Examine the velocity versus time graphs predicted by your models with and without drag. Do any of your models predict the terminal velocity? If the answer is no, what similar experiment could you design to find the terminal velocity of your object? Discuss briefly. No, none of my models predict the terminal velocity because the paper wad never had 0 net force throughout the entirety of the motion. This is clear because for there to be 0 net force, there would be constant velocity, and the velocity in the y direction is never constant with and without drag. An experiment that I could design to find the terminal velocity of the wad could be to drop the paper wad from a high height so that it reaches terminal velocity before hitting the ground. This is because it would eventually experience free-falling motion. What if? Imagine if the object were initially thrown straight up and with the same initial speed as in your experiment. Would the time this object take to reach the ground be the same, longer, or shorter than the time it took in your original experiment? So if the paper wad was initially thrown up with the same initial speed, it would take longer than the time it took in the original experiment to reach the ground. Because this in the case of the projectile motion, using the equation v final y is equal to v initial y sine theta plus f net over m delta t, and then manipulated to solve for delta t. Knowing that the velocity is 0 meters per second at the peak of the trajectory, delta t is equal to v initial y sine theta over g. Multiplying this by 2 to get the initial time of flight, we get delta t is 2 times v initial y sine theta over g. So in the scenario of the paper water being thrown straight up, the delta T is 2v initial y over g. Because there's no angle that the water is thrown up at, that's why it's 2v initial y over g. And 2v initial y over g is always greater than or equal to 2v initial y sine theta, thus it will take longer to reach the ground. And that's the end of my presentation. Thank you.